What if I told you there is an object in the universe so dense that matter itself gives up resisting, a place where atoms collapse, electrons vanish, and gravity presses so hard that the concept of solid no longer applies? You wouldn't fall into it, you wouldn't orbit it for long. If you touched it even for a fraction of a second, your body would be flattened into a thin layer of particles spread across its surface before pain could even exist. In movies, when massive stars die, they usually become black holes. Dark, final, inescapable. But black holes are not the only ending. There is another outcome, less famous, less understood, and just as extreme. If you somehow found yourself standing on a neutron star today, what would you actually experience before everything ends? Let's find out. For most of the 20th century, neutron stars were purely theoretical. Scientists suspected they might exist, but the idea sounded almost absurd, matter-packed, so tightly that atoms themselves collapse. It wasn't until 1967 that reality caught up with theory. That year, a graduate student named Jocelyn Bell Burnell noticed a strange signal in radio telescope data. It was a pulse, then another, perfectly spaced, more accurate than any clock humanity had ever built. At first, scientists jokingly labeled the signal LGM, little green men, because nothing natural was expected to be that precise. But the truth was far more extraordinary. The signal came from a rapidly spinning neutron star, a pulsar. Neutron stars are born in violence. When a massive star reaches the end of its life, it runs out of nuclear fuel. For millions of years, fusion in the core had pushed outward, balancing gravity. But once the fuel is gone, gravity wins. The star collapses inward in seconds. The outer layers rebound violently and explode outward in a supernova, briefly outshining entire galaxies. What remains behind is the core, crushed, compressed, and transformed. If the core is too massive, it becomes a black hole. If it's slightly less massive, it becomes something else entirely. A neutron star. During the collapse, gravity becomes so intense that electrons are forced into protons, creating neutrons. Individual atoms cease to exist. The star becomes a single, gigantic atomic nucleus held together by gravity itself. The result is an object with the mass of our sun compressed into a sphere roughly 20 kilometers wide. To put that into perspective, if you compressed Mount Everest into the size of a sugar cube, you'd get something less dense than neutron star material. A single teaspoon of neutron star matter would weigh billions of tons on Earth. There is nothing denser in the universe that we can directly observe. Gravity on a neutron star is around 200 billion times stronger than Earth's. If you could somehow approach its surface, your body wouldn't be torn apart like in a black hole. Instead, you would experience something called spaghettification in reverse, extreme vertical compression. Your feet would feel gravity so much stronger than your head that your entire body would be flattened instantly. You wouldn't scream, you wouldn't feel heat, you wouldn't even register fear. Your atoms would be forced into a paper-thin layer across the surface before your brain could process the moment. And that's assuming you survived the approach, which you wouldn't. Neutron stars are incredibly hot, with surface temperatures reaching millions of degrees. They emit intense radiation, including X-rays and gamma rays, powerful enough to sterilize anything that comes too close. The vacuum around them is flooded with lethal energy. But gravity isn't the only thing that makes neutron stars strange. Time itself behaves differently there. According to Einstein's general relativity, the stronger the gravity, the slower time flows. On the surface of a neutron star, time passes noticeably slower than it does for someone far away in space. A clock placed on a neutron star would tick more slowly than a clock on Earth. Neutron stars also rotate at mind-breaking speeds. When a star collapses, it spins faster, conserving angular momentum, just like an ice skater pulling in their arms. Some neutron stars rotate hundreds of times per second. These rapidly spinning neutron Stars are called pulsars. As they spin, they emit narrow beams of radiation from their magnetic poles. If one of those beams sweeps past Earth, we detect it as a pulse. That original signal from 1967. It was a star spinning like a cosmic lighthouse. Pulsars are so reliable that astronomers use them as natural clocks to test Einstein's theories and even search for gravitational waves. Some pulsars are accurate too, within a billionth of a second. Then there are magnetars, neutron stars taken to the extreme. Magnetars possess the strongest magnetic fields ever observed in the universe. Their magnetic power is trillions of times stronger than Earth's. If a magnetar passed halfway between Earth and the Moon, it could erase the magnetic data on every credit card on the planet, get much closer, and the magnetic field would begin to distort the electron clouds of atoms in your body, literally pulling you apart at the atomic level. Occasionally, magnetars release sudden bursts of energy called starquakes. In just a fraction of a second, a magnetar can release more energy than our sun emits in hundreds of thousands of years from across the galaxy. These flashes can briefly affect Earth's atmosphere. Despite their power, neutron stars exist on a knife's edge. They are held up by something called neutron degeneracy pressure, a quantum mechanical force that resists further collapse. But this resistance has limits. Add just a little more mass, perhaps from a nearby companion star, and gravity overwhelms even neutron pressure. When that happens, the neutron star collapses further. Space and time curve more deeply. An event horizon forms. The neutron star becomes a black hole. In that sense, neutron stars are not just objects. They are thresholds. They represent matter pushed as far as physics allows, balanced perfectly between existence and annihilation. They show us what happens when gravity nearly wins, but not quite. So while black holes may capture our imagination, neutron stars may be even more unsettling. They are real, they are observable, and they demonstrate that the universe doesn't need fiction to be terrifying. Sometimes the most extreme objects are the ones that almost, but not quite, disappear. If you enjoyed this deep dive into neutron stars, there's much more to explore, from black holes and time